All right, so let's try this with a sample size that's not equal to 1. So let me close this. Let me go back to our little generator, and I'm going to add one row and add one column. So now every click is actually 4 coins being flipped. Now notice, before we let Jump do this simulation, what types of sampling error we're getting. In this situation, where I had 3 coins coming up heads and 1 coming up tails, the mean is 0.75. When I click it again, in this case, I actually got a mean of exactly 0.5. That's 2 coins coming up heads and 2 coins coming up tails. As I click this, you can see the different values that this process, this sample of size 4 with 4 binomial processes, you can see the values that it can take on. It can take on values 0, 0.25, 0.5, 0.75, and 1. Now let's see what types of sampling error over the 100,000 samples we're going to get. And specifically, let's look at the distribution of that sampling error. Now to do this, let me go back to the Jump data table. Let me right-click the mean of n equals 4 column. And let's first look at how we're going to get Jump to actually do this process. That is, how we're going to get it to relate to these 4 little blocks or 4 flips of the coin. So under the formula, you'll see what I've done. Instead of having just one random binomial in the numerator, I now have 4 of them. And so these 4 of them are going to be added up. That is, we take the sum of the 4 random processes, and then to get the mean, we're going to divide that sum by 4. So this is really related to exactly these 4 little blocks. Each of the random binomial processes in the numerator is one of the blocks that I have on the left. And every row in the data set, thus, will be the 4 blocks being sampled and then divided by 4 to get the mean value. So every row in the Jump dataset is in essence this mean. Let's see what types of observations we get, and specifically the type of sampling error we get. I'm going to right-click this mean n equals 4 column, and I'm actually going to go back to hide unhide. This will add it back to our dataset. Let me clear the selection, and let's take a look at this using the distribution platform. Again, go to Analyze Distribution, but this time take the mean n equals 4 column and put that into the Y role. Now right away, you can see something has changed with the distribution we've observed. No longer are we simply getting 1s and 0s for each sample. Again, we can observe now 5 different values, a 1, a 0.75, a 0.5, a 0.25, and a 0. In fact, a large proportion of our samples actually hit it spot on. And remember what hitting it spot on means. This means we actually observed a sample whose value was equal to the expected value. The expected value of any coin or binomial process is 0.5, so we actually had a significant number of our samples that hit that exactly. But we also had samples that didn't get it right. Some of the time, we got samples with 3 heads, sometimes with 4 heads, sometimes with 1 head, and sometimes with 0. So the types of sampling error we observed here, sometimes 0.25 from 0.5, sometimes a half from 0.5, and sometimes negative 0.25 and negative a half from the expected value. Now before we leave this simulation, let's also observe something else about this distribution. First, it's symmetric about 0.5. That is, we're just as likely to observe sampling error in the positive direction as the negative direction. This should make sense. There's nothing special about getting heads or tails here. We're simply observing coins flipping. So it's just as likely to get a bunch of heads or a bunch of tails. Second, you'll observe that the shape of this is no longer those 2 flat squares, right? We actually have something that looks kind of triangular. That is, sampling error falls off. It's most likely that we're going to get a 0.5 for each sample, and it's least likely that we're going to get all heads and all tails. Notice this, it's not as likely to get all tails as it is to get 2 tails. So the insight here is that extreme amounts of sampling error are less likely than smaller amounts of sampling error. Now let's try this with one more sample size, that is, samples of size 100. To do this, what we're going to do is add up to 10 rows and columns to our little simulator. So 5, 6, 7, 8, 9, I have to make this a little smaller. 8, 9, 10, so 10 rows. Let's add up to 10 columns, and this will give us a grid of 100 little binomial processes. And every time I click this button, remember, each one has some probability of taking on a value of 1. That is, each one has a probability of a half of hitting heads. So every time I click this button, each of these little random processes is independently being flipped. And at the end, we'll take a total and divide that by 100 to get our mean. Okay, so how are we going to get Jump to do this? If I right-click on the mean of n equals 100 column and go to the formula, you'll notice that I did something differently than the previous columns. Rather than actually copy and paste individual random binomial functions 100 times, I'm simply utilizing something about this formula. That first argument, the one that asked me to take a value of n, here it says without the value in it just asked me for n, this is in essence asking me how many flips of a coin would you like to do? Instead of just doing one and copying this whole formula over and over 100 times, I can simply enter in 100 so that this entire top portion, this one little random function, is actually representing this entire grid. So notice that relationship. This entire grid, the sum of it, is modeled by this one function. And then to get the mean, remember we're looking for the mean of these 100 random processes, we're simply going to divide this total by 100 to get the mean.